All right, so we are in our last week, week 10. And we've covered effectively everything that I was hoping to cover, with a few straggling topics here and there, but all the major topics we've basically gone through at this point. So my plan for this week, for Thursday, is to mainly concentrate on review for the final and any lingering questions that you might have, and so on and so forth. But definitely not planning on any new stuff on Thursday. For today, I'd like to just keep hitting Verilog. I'd like to talk about the labs, any questions that you have, and just kind of like wrap up that part of things. But there's a lot we can still do on the Verilog front. We kind of rushed through the second part of Verilog on Thursday. So the first part was working with the Icarus system, which was writing Verilog code, compiling it, simulating it, looking at the waveforms with GTK wave. And then the second part is actually being able to take your design and push it out to an FPGA board. And we blew through that really quickly the second half of Thursday, and got a design uploaded. It did not work. I fixed it like 5 minutes later, and I posted a note on that. But we'll wrap that up with some hardware, and just go through some of the things with that tool chain for simulation, and so on and so forth. I've also got some show and tell to pass around, and if we have time, I'll probably do some Minecraft with you and look at digital logics in Minecraft, because it's an interesting, different view of how all this business of logic gates and sequential elements and so on comes together. So questions from you up to this point, things that you're working on, things that you've given up on, or anything like that. Labs. Lab 7 is still, I'm missing it from about half the people still. So, but at this point, I'm only going to take off 1 day penalty for being late, because I really want everybody to turn it in. Yeah?
For Lab 8 experiment 2, I just don't really understand what declare a count as reg 29-bit 0 means.
Yeah, so experiment 2 is a whole quantum leap beyond what we've done. So let's look at that particular statement, and then maybe we can talk about this more generally too. So experiment 2, we're building a counter, right? Basically, we're building something that's going to count up from 0 to some point, and then when it reaches that point, we're going to toggle an LED, a variable, right, between a 1 and a 0, and we're going to use that to turn an LED on or off. So what's the exact state of reg? Okay. So here's the setup. On most FPGA boards, there's a clock provided for you. Okay, because most of our circuits need a clock to work. We're mostly building state machines, and state machines are driven by a clock. So as I mentioned last time, this little metal canister right here, this is probably a quartz crystal. It has a resonant frequency, and we can use that to generate a very stable clock. Okay, so this generates a pulse at 100 megahertz. So it goes up and down and up and down, 100 million times every second. Okay, so this distance from here to here, 10 nanoseconds. So pretty fast clock compared to what we've been working with in the labs with our 2-second 555 and so on. And this is available inside the FPGA. The output of this clock circuit is fed to one of these pins. Okay, just like these push buttons are fed to pins, just like some pins are feeding into these LEDs. The output of that clock is available on pin 126. So in our user constraint file, the UCF, if we put in a line net clock loc equals P126, whenever we refer to the variable clock, it's automatically changing for us. Okay, this is in the actual hardware. So how do we turn something on and off every half second, well, we basically count clock ticks. So we're going to build a module that basically takes in this clock and generates some output. We'll just call it LED out. And here's the behavior that we want. We want LED out to toggle every 50,000 ticks. So every 50 million clock ticks. Well, how do we know when 50 million clock ticks have passed? There's really only one way, which is to just count the clock ticks. Ticks, there's 1, ticks again, there's 2, ticks again, there's 3. And every time that you get a tick and you increment this counter, see if it's equal to 50 million. And if it is, change the state of the LED output and then reset your count to 0. So to do that, we need some kind of variable. We can think of it as being called count. And it's got to be able to hold values from 0 up to 50 million. So it's got to have a bunch of bits to it. Right? Now we could probably safely just make it a 32-bit register because we know 32 bits counts up to 4 billion. But if you want to be a little more precise about it, a million takes 20 bits, and 64 million would take 20 plus 6 is 26 bits, and we don't have to go quite to 64 million. So I recommended 26 bits. Oh, I made it bigger though. Huh, okay. That's fine. 26 bits is enough, but what I recommended was making it a register that'll hold 29 bits. I think I just left some wiggle room in there. So if you say something like register bracket 20, what did I do? 28 to 0. Alright, so this is actually holding 29 bits. So you're making a really big wide register, right? If you just say register X, X is basically a flip-flop. It holds 1 bit. But if you say something like register 2:0, some variable name like state, we're saying state has to hold 3 bits. And you're probably going to get 3 flip-flops. And one of them might give us state 0. The second one will give us state 1. And the third one will give us state 2. So when we say register 28:0 count, we're really saying I want 29 flip-flops. And I'm going to call that collection of flip-flops count, and I'm going to refer to the first one as count bracket 0, count bracket 1 is the second, and so on. But other than making this declaration, we don't really need to know that this is 29 flip-flops. To us, it's just kind of like a variable in a programming language. It's a thing that can hold a really big value. Okay, in this case, up to about 500 million. And we can do things like this. And it will synthesize, the tools will synthesize for us a 29-bit adder, and it'll feed 28 zeros followed by a 1 into the A input, and it'll feed the outputs of these 29 flip-flops into the B input, and it'll take the sum coming out of the bottom and load that back into the D input, and when the clock ticks, count will be incremented by 1.
So when it hits 50 million, do we just hit like our reset?
Yeah, so we can say something like if count equals 50 million, set count to 0.
Gotcha.
Else set count equal to count plus 1. And this was one of the things we did on the board last week, right? You implemented, I think, a 3-bit counter from 2 to 5 or 2 to 6 or something like that. And it was the same idea. If your count was equal to 6, we reset it to a certain value. Otherwise, we just set it equal to its current value plus 1. So that's what that's referring to in there, in the lab, declaring count as a register. Does that make more sense? Okay. And we can run through this in class in a little bit because it's a good practice exercise. Had a few questions from people on their labs about test benches versus the module that you're testing and sort of keeping those straight and what happens in each one. Imagine that you're planning to program an FPGA, right? And you're trying to build something that, you know, makes the LED blink or reads your switches and does some logic operation and lights an LED or something like that, right? The code that you're writing, the Verilog module, to actually perform that function, that's what we can call a unit under test. Okay, UUT. That's the thing that you're trying to actually design. Okay, the test bench is a software version of this platform, right? It's a way to simulate button presses and LED outputs and clock inputs and things like that. And the idea is, here's your test bench, right? Here's your unit under test. It gets dropped into somewhere inside your test bench. And the test bench is setting inputs and it's reading outputs and it's setting more inputs and it's bumping a clock up and down and so on and so forth. So the test bench is basically, I mean, it's literally a wooden bench with test equipment on it that you take your circuit over to and you plug in power and you plug in the frequency generator and you hook up the oscilloscope, right? That's a physical test bench. This is a software version of it. So the test bench is the thing that you're plugging your unit under test into in order to see if it works, see what it does. And if you're programming an FPGA, ultimately you get rid of the test bench and you just have the module, the adder, or whatever it is that you're going to dump into here and use to control your traffic light or your self-driving car or whatever else you're doing. So other questions?
I don't really have a question. I can't get my third experiment to compile.
The traffic light?
I think so.
Lab 7 or, I mean,
No,
Lab
the
7 or
mood-
Lab
the
8?
mood.
The mood machine.
Yeah.
Is it giving you specific errors?
I haven't looked at it since this weekend, so I have to look at it again and talk to you later.
Okay. Yeah, definitely, because it will tell you where the problem is. And sometimes it's as simple as a missing semicolon somewhere, right?
Yeah.
Sometimes it's something more subtle. For example, say you do always at pause edge clock or something like that. Begin. So this is a reasonable looking code to write. If the reset input is asserted, let's set the count to 0, and then let's increment the count. So normally this just bumps the counter up by 1, but if you say reset, it'll clear the counter first and then set it equal to 1 probably. This will give you synthesizer errors. Syntactically it's fine. right? It's valid Verilog statements, but in terms of the semantics, the meaning of this, you'll get errors later on as you try to synthesize because you're trying to give count two values at the same time. If count is equal to 17 and reset is set, this is saying load a 0 into count, this is saying load an 18 into count. Right? And they're both being done at the same time because everything is parallel. And you can't build a piece of circuitry that will load two values into your flip-flops. It's physically not possible unless it's a quantum Verilog system or something. So you'll get synthesizer errors from that. So sometimes it's syntax issues, sometimes it's something more subtle, sort of down
I think that's what it
the
is.
tool chain.
I have a picture, I'll try and write it on the board during the break.
Okay, cool, awesome. So let me do a bit of show and tell, just so we can pass these things around while we're doing other stuff. So,
Big one.
so this is another FPGA board. I guess it technically goes like that. Doesn't matter. So this is a Xilinx FPGA. It's a Spartan 3. This is a Spartan 6 in here, so it's a bigger FPGA. This is a Spartan 3, much older line. But it's got more bells and whistles. It's got little slide switches over here. It's got 6 push buttons. It's got 3 7-segment displays. This is a VGA port up here, audio port, micro SD port, and then just tons of things that you can connect to. So all of these are connectors that are available to plug into, and you can read and write those. There's 8 LEDs along here. And it's a general sort of development board. Exactly the same software tool chain, right? You go into the Xilinx software and you write your Verilog, and you use a different configuration file to say, okay, I want this input to come from this button, and I want these 5 outputs to go to these 5 places on the VGA controller, right? But you write your Verilog for your module and you dump it in and it does whatever it does. Yeah.
What is this compared to like a Raspberry Pi? It seems almost similar.
Yeah, good question. So how many people here have heard of a Raspberry Pi? How many people have played with one? So you get to do this, if you're CS, you get to do this in the 200 level CS courses starting in fall. So Raspberry Pi is a standalone Linux machine, basically. Well, it's a standalone microcomputer, but usually runs Linux. So it's got an operating system, it's got a file system, it's got peripherals like a video display, Bluetooth, place to hook up keyboards and all sorts of things like that. Okay, it's a full-blown computer that you can just take and use. This is bare hardware, right? You can plug a VGA monitor into this port and it does absolutely nothing, right? The only thing that this is connected to is a handful of pins on the edge of the FPGA, right? The only thing the micro SD card does is connect a few pins to some pins on the FPGA. It does nothing by itself, but you can make it do almost anything by configuring the FPGA in the right way. So you can turn this into a Raspberry Pi, and if you were designing your own version of a microcomputer, you would probably do it on something like this first, pinned on the design, and then maybe, you know, just sell FPGAs that are programmed like this, or pay the upfront costs and actually have a custom chip made. But it's really blank hardware. And the use case for each of those is very different, right? If you aren't too worried about speed and you want to get something up really quickly, you probably write a program and you run it on a Pi. But a Raspberry Pi or any computer is a really slow piece of hardware because it does basically one thing at a time. And every time the system clock ticks, it starts to read an instruction from memory, it interprets it, and it executes it. And it does that one step at a time. Whereas this, right, you can do millions of things in parallel. And so it's potentially a lot faster, but it's harder than just writing a program. Right? If you want to sort 100 numbers, you can write a bubble sort in 10 lines of C. If you want to do a bubble sort on this, that's a huge undertaking, right? Because you got to design it basically from the transistor level or the gate level up. but that's not as bad as you might think. So let's see if I have a network connection first of all. I'm just going to disconnect and reconnect for good luck. So there's a website called opencores.org. This has been around forever, not literally, but effectively. So what's a core? A core is a chunk of typically Verilog or VHDL code that implements some functional piece of hardware, some particular aspect. And open cores is a project to sort of have open source versions of hardware modules available to the public. So open source as in you can freely access and use the raw code, right, the actual Verilog or VHDL code, and certain conditions on redistributing it, commercializing it, and so on and so forth. But an open source mindset. So if you come to projects, these are some of the categories of Verilog, or hardware definition for modules that are available. So if we just click on processor, I haven't looked at this site in a while. 16-bit microcontroller. This is licensed under GNU public license, so it should be completely free. This is VHDL. I don't want to look at VHDL. Let's see what else we got. That's VHDL. That's in C++. That's weird. We'll look at VHDL if I don't find one soon. All right. So these are projects people have done, right? Oftentimes just individuals who decided, hey, it would be cool to make a 16-bit microprocessor using an FPGA. And so they've written the code for this and they've shared it with the world with various other things. So I don't know if I can actually get to these. Yeah, we can download. Oh, you need to log in. Okay, I have an account, but I don't remember what it is. So what's available on here? So microprocessors, right? 32-bit processors. There's a Z80 processor. That's a really old processor line that was used in the TRS-80, if you've ever heard of that. Radio Shack's version of a PC. 4004, that was the original microprocessor. That came before the 8008, which came before the 8080, which led to the 8086, which is what we're still using today, basically.
So are people reconstructing old CPUs on
In some cases,
FPGAs?
yeah.
Just see how they work?
Yeah, either as an exercise to see how it works, or because you want to do something with an x86 architecture, and you don't want to actually get Intel chips or AMD chips and wire them up and deal with them. You want to just embed it inside some bigger project. So you take a little corner of your FPGA and you build a microprocessor in there. And now you got the best of both worlds. When you want to do your bubble sort of 100 numbers, you write a little bit of code and put it on that simulated processor. But when you want to do video processing or signal processing from an audio source or something, you write the custom hardware to do that. And you put these together. So yeah, oh, here we go. Apollo Guidance Computer NOR emulator. So that's nice. So tons of processor. System on chip is the idea of taking a bunch of different modules and putting them all together on a single chip, kind of like I just said, CPU plus some custom hardware for video processing and so on. instead of a motherboard where you have, old motherboards, you had 15 different things going on in different pieces of the board, throw that all into a single chip, right? And in this case, just implement it on an FPGA. So video controllers, JPEG decoders, those little 2-line LCD displays. There should be some VGA drivers in here. Yet another Verilog VGA, yet another VGA, and so on and so forth. And this is all available, right? So if you're working on a project, so like I mentioned before, people were using FPGAs for Bitcoin mining a few years ago. That was like the big thing. Well, you don't want to spend your time figuring out how to write Verilog to do division, right? Or to do prime number detection or something like that. You find a core that already does it, and then you add your own kind of secret sauce to it. Crypto cores, right? You can write your own crypto system, but there's tons of options out there already. People have already done this work. This is the same game we get into with computer programming, right? Particularly in more object-oriented languages like Java. You want to take an image and turn it into a JPEG. Well, you could look at the JPEG standard and you could figure out exactly how to do that and write code for it, but you probably wouldn't unless you were doing it because you were interested in it, because there's already modules that do that, right? If you want to add speech synthesis to your program, you pull down a speech synthesis module and you just plug into it. Same idea here, but with hardware. So the other advantage of things like Verilog is that you have access to this huge base of knowledge that you can just sort of grab and build on top of. And that's pretty cool and really fun to work with. So arithmetic systems, so array multipliers and complex arithmetic operations, prime number or random number generators, and so on and so forth. An FPU is a floating point unit. That's the real number version of an ALU, an arithmetic logic unit. And that's a block of hardware that basically does add, subtract, multiply, divide, and maybe some things like trig with real numbers. So floating point. Have we talked about floating point numbers in this class? Oh, my bad. We're going to have to do that after break. That's a good topic to see. All right, so Open Cores is a fun site, but like I say, it's a general kind of concept. So let me pass this one around. And let me just show you a few other goodies. So this is similar. This is by a company called Digilent. It's still a Xilinx product. The FPGA is Xilinx. Digilent is the company that makes this board, right? And same idea. You've got slide switches, push buttons. You've also got an Ethernet port here, plus an HDMI output. So if you want to write an HDMI display driver, right, you can write Verilog for that or download it and hook up there. More audio input and output, and so on and so forth. So this box showed up in the mail a couple of years ago at my house, and my advisor was cleaning up, so he sent me a bunch of his old boards. This one is a different company, so this is a company called Ltaro. So Xilinx and Ltaro are the two main FPGA companies today. Ltaro was bought by Intel pretty recently this year. So that's an Ltaro FPGA, but basically similar to the Mimas board we've been using. I/O lines along the side that you can access, a few push buttons, some really tiny slider switches down here, and that's about it. Everything else is up to you. The thing about Ltaro is it's a totally different tool chain, because you use the software tools from that company instead of from Xilinx. But the same basic idea, the same basic steps, the same basic tool flow of enter your design, check the syntax, compile it, go through the various steps for synthesizing, create a programming file, download it into the board. this is probably the funnest looking one at least. This is another Ltaro board. And it's got big buttons, so it's got to be better, and it's got the red button, of course. But lots of connectors on the side, right? USB ports, audio, S-video, VGA, Ethernet, general GPIO connectors, and I think that's about it. Oh yeah, and 6-7 segment displays. So, and all of these, they're kind of the same deal. You find the documentation. Mostly you find a schematic, so you can see what's connected to what. You find a constraint file that you can work from, so that if you want to drive this segment on this display, you know that's coming into pin 312. And then you say, okay, pin 312, I'm going to call that Q. And now if you set Q to a 1, that segment lights up. And if you set it to a 0, it turns off. And you kind of go crazy with that. So let's go back into the Xilinx software. So what did we call this thing? XR Gate Engineering 250. So this was our code that we wrote on Thursday. And this was the constraint file. And the problem on the constraint file, like I mentioned in that announcement, was that on X, which is an output, for some reason I had a pull-up down here, right? And that's basically saying, let's take the output and let's connect it to power through a resistor. And that's sort of conflicting with the idea of an output. So it was refusing to actually connect that the way that I wanted. So it was making it what's called a tri-state output. So the output was basically floating. That's why the LED wasn't turning on. So if you take that off, and then go ahead and build this. So we've got our programming file. So that's already set up. Let's go ahead and program this. Yeah. so that verifies. Thank you. So, that's fuzzy. All right, so this is an OR gate. If you press one switch, the LED comes on. If you press another, the LED comes on. If you press them both, it goes off. And if they're both switches are off, the LED goes off. So what kind of gate is that?
Exclusive OR?
That's an exclusive OR, right? Which I guess I changed the code. Right, so if A is not equal to B, it sets the output equal to 1. Otherwise, it sets it equal to 0. Right, so that's an XOR. If we do that, it's going to be equal to 1 if A and B are both equal to each other. So your truth table is going to look like, let me go ahead and start this build. Your truth table is going to look like this. Right, if A and B are equal, it's going to output a 1, otherwise a 0. So what is that logic gate?
NOR?
What kind of NOR?
Exclusive.
Exclusive NOR.
And a regular NOR would just be only 1, 1.
Yeah, well, it would be anything except 0, 0. And regular ORs are sometimes called inclusive ORs. You'll see that terminology in 270. So we make that one change. We set it equal to 1 if A and B are equal. We did the rebuild of the whole module. We click on Generate Programming File, which is usually pretty quick. And then we come over here and we just reprogram the board. So that's programming, and it'll take a minute to write in and verify. When it's done, since neither switch is pressed, that second LED should turn on to say the output is a 1. And now it's like, how long do we wait before we check to see if it finished? I'm going to give it 30 seconds, because I'm confident. As soon as I change, it's going to come on. There we go. All right, so both switches are off. Either switch pressed, the LED goes off. Both presses, and it turns on because it's a 1, 1. So there's your exclusive NOR. Yeah.
And does that update every clock tick or as soon as the button's pressed?
There's actually no clock in this module at all. Now the clock is still running, right? And it's sending this 100 megahertz signal to pin 126, but we're not using pin 126, right? So it's kind of a non-event for us. Curious whether I can get into something here. So let's play with the clock. So let's do File, New Project. We'll call it Engineering 250 Blink. And all of this should still be set up from last time, so I'm not going to change any of that. And I'm going to say New Source, and I'll make a Verilog module. I'll just call it main. And let's have one input A. And let's have an output called LED. No, let's not even bother with an input. Well, yeah. We'll have our input clock, and we'll have an output LED. And I'm going to want a user constraint file. So I'll say new source, implementation constraint file. I'll just call it pins. And I'm going to rip off the code from our last project. So the clock coming in is on pin 126. It's the 100 megahertz clock. And I forgot where I put the LED. So what's our output called? LED. Right, so what are we doing here? We're connecting the variables in our Verilog code to actual pins on the FPGA. So I'm saying the clock's going to come from pin 126. We know that's an actual 100 megahertz clock. And LED is going to come from pin 118, which is going to go to pin 118, which is connected to the second LED. So let's count clock ticks. So when the clock ticks positive edge, we're going to do the following. Let's set the count equal to, I don't know, 50 million. Yeah.
How come this won't give us the same error you were talking about before, where it counts as two different things?
Because it's only going to do this or this, because I've got them inside this if-then-else statement. So if this condition is true, it'll initialize count to 50 million. Otherwise, it'll decrement count. So it will build hardware so that only one of these values goes into the inputs of the flip-flops that make up count. So it'll be happy synthesizing that. So here we're counting down instead of counting up, no real difference. We count down when we hit 0, we reset to 50 million. Otherwise, we just decrement. So every 50 million clock ticks, this piece of code will trigger. So let's just set LED equal to the complement of LED. So that should alternate between ones and zeros. And so there's the end of our always block. So this should be a blinking LED. Right, this should count down from 50 million, and when it gets to 0, it should toggle the state of the LED. So let's see if this works. Did not work. Uh-oh, we did something bad. So it says procedural assignment to a non-register is not permitted. Left-hand side should be a reg, integer, time, genvar. So that's pretty specific, right? And remember, we said that inside an always block, when you assign to something, it's probably got to be a register. Because this is not an assignment statement, right? We're not connecting LED to something. We're saying load this value into LED. And we can't do that if LED is a wire, and wire is the default. So we really need to say register LED. So those error messages are usually pretty helpful, but not always. Sometimes it's totally cryptic. And then you got it.
Allocating it space in memory.
Say again?
You're just allocating it.
I'm asking it to create a flip-flop, basically, which is the same thing as allocating a space in memory, but there is no pre-existing memory, like with a regular computer program. So we're saying, okay, we're probably going to need a flip-flop to hold this variable LED. And then down here, where we say LED is not LED, it's taking the output, running it through an inverter, feeding it back into the D input, and then connecting the clock to whatever the clock is in that always statement. So that compiled and it's synthesized, and we'll create a programming file. Oh, and I forgot to do the secret process properties, which is create a binary configuration file. So we'll do that and rebuild it. So there's a bit file and there's a bin file. I don't know what the bit file is used for, but that's the default. But we need a bin file. They're two just different versions of the same information. So now we can come here and we can browse to well, what did we call this thing? Engineering 250 blank. And we want the bin file, and let's program the board. We'll take a break after this. And guess what? It's not blinking. Sadness. Don't think it's about just unplugging it. All right, so 5-minute break, and we'll make it blink.